Hey there! Let's talk about linear, quadratic, and exponential models and how you can compare them and tell the difference if given a table, like so. So let's analyze this. We have x equals 1, 2, 3, 4, and let's just keep a note here. They're adding by 1, so it's a constant rate. Now for linear, as x goes up or y goes down. And it's always constant because our equation here is y equals mx plus b, and m is our constant. So we need to have a constant, otherwise it wouldn't be such a straight line. It would be more like a U or a zigzag. And let's compare the y now. So y would be 2 and 4, 2, 2, and 2. And it is indeed constant, so this would be a linear model because they're both constant variables. And now if we're looking at quadratic, let's look at this one, and this one is quadratic. And if we look, x is still the same, plus 1, and plus 1. But y here is a little different because from 1 to 3 we have a difference of 2. From 3 to 9 we have a difference of 6. So that's already not very constant. So we know it's not linear. And 9 to 19 is 10. But if we take a closer look into this equation, this table here, we can find out that there is a deeper difference. Not the immediate constant, but if we look into it, we can see that 2 and 6 is 4, and 6 and 10 is 4 as well. So actually, the second difference is the constant for quadratic models. Now, why is that? Well, it's mainly because the basic equation is that it's squared, which means that difference is kind of like representing each square. The first difference is for a singular power, the second difference is for a square, and if we look later, a cubic function would be the third difference, and so on. So that's this one, and now let's look at exponential models. Here's the final form that we're going to look into, which is exponential models, and same thing, x equals 1, x equals 1, x equals 1, and if x wasn't equal to 1, we would probably have to look into that as well. But just for this purpose here, we're going to make it x equals 1 for the difference, first difference. And for y here, we know it's not linear, it's not quadratic, so it has to be something different, right? So 2 and 4 is 2, 4 and 16 is 12, 88 and 16 is 72. Now, if we think about it, first instinct, let's try, well, 2 and 12 is 10, and 12 and 72 is 60, and that difference is 50, and, well, that doesn't look right, because if we keep going and making this list longer, we know that the next difference isn't going to be 50, and it's not going to work out, really. But the actual thing about this that makes exponentials so special is that it's a multiplication function. So the difference is actually times 6 and times 6. Instead of adding, it's multiplying. And that's the main difference. That's why it's different than the rest. So because the main function is y equals, let's say, x to the 2 to the x power. So it's really different from the rest, and there's a clear understanding that a function that is exponential goes just straight up, just all the way up, and it's a lot faster than a normal function, and that's why it's exponential. So we've looked at all three, and let's compare some of the differences that we've seen. So these are the three models we're looking at, and the main thing you can tell from each of these is that linear is just simple. You can immediately spot it. The first difference is immediately constant, and for quadratic, you have to do a little more work, but after this difference, you can immediately see that it's also constant. So the second difference here is the one constant, and this is the first. And for exponential, at first you'll be thinking, what on earth is this? But break it up and you can see that, well, there's nothing that can actually work into this except a multiplier. So times 6 times 6, and this is times 6. And those are the models that we're going to look into. Now let's apply these into word problems and see how we can find out what it is. So these are 3 problems that we can apply these concepts to. Mac goes on a 3-mile walk every single day. This week he wants to increase his walk by 1 mile every single day. We know that the constant is 1 mile because he wants to increase it every single day. So if we start off with 3 on Sunday, then 4 on Monday, 5 on Tuesday, 6 on Wednesday, 7 on Thursday, 8 on Friday, and 9 on Saturday. Something like that. So because it's steady and it only increases by 1, we know that this is linear. And to write this equation, we use y equals mx plus b. For the next one, Sally shoots a paper airplane with an initial velocity of 50 feet per second, starting from her height of 6 feet. Calculate how long the ball will be in the air. These problems, it's kind of a little harder to see what it is at first, but you know that normally, because a parabola is a U shape, it's normally upside down or right side up. These problems normally have to do with shooting projectiles into the air or firing something, making something fly, or a bridge. And here we have initial velocity, so we know that it's going to start and go up, and when it goes up it has to go down, so we know it's a quadratic word problem. And this would be quadratic, and we would use y equals ax squared plus bx plus c. For the last one, carbon-14 has a half-life of 5,730 years. Professor X has a 150-gram sample of carbon-14. Find how long much of the sample is left after 100 years. We know that a half-life, if you haven't covered that, a half-life is basically 1/2 the life, which is 5,730 years. Professor X has a 150-gram sample, and you know that it's going to halve. That's what a half-life is. It's going to halve by over a period of time, it will decrease, but it will decrease by halving itself, which is kind of like doubling, and that's what we're doing with exponential functions. It goes straight from all the way up to 4, 16, 32, and so forth. It's really fast, and that's why this is exponential, because it will rapidly halve itself, and pretty soon it'll just disappear. And the basics for here is y equals, let's say, 1/2 abx. Normally it's just the ab, so we can just say this is the basic right here. And normally for exponential functions, we would have normally something that doubles really quickly, like bacteria, or we'd have a half-life, or if we're doubling, and some other really common ones are population growth, or investing in money for a bank that compounds, or the cost of a car that's depreciating. And that's all for linear, quadratic, and exponential models. Thanks for watching this video, and this video has been provided to you by SATFreePractice.com.